Hello, welcome back. Today we're going to continue our discussion about Taylor series. Now, yesterday's lesson we learned how to write sine of x, and we said we can write sine of x as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And of course, this goes on forever. That's what those dots mean right there, that this is just going to keep on going forever. And remember, this is different than a Taylor polynomial. In a Taylor polynomial, we would say sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And we stop. Because a polynomial only approximates to a certain degree. Where a Taylor series, because this pattern goes on forever, actually this polynomial becomes the function. And I got a really funny joke for that. What did the function say to the Taylor series? Stop copying me. You get it? Because the Taylor series copies the function. So today's lesson is why we care about a Taylor series. That's what we learned last night, and what we're going to do a little bit more today. For instance, why is it important that we can write sine of x as a polynomial? Well, the main reason is trigonometric functions lack finite algebraic formulas. In other words, I can't write them as like an algebraic formula. So a series gives me the next best thing when I'm looking to solve them or integrate them or just basically using a trig function. A power series can allow us to find an approximate but very accurate values of trig functions as well as other transcendental functions. And you might remember yesterday we did e to the x. So let's take a look at our example here. We're going to use the Maclaurin series. Maclaurin, we love Maclaurin. Hi, I'm Maclaurin. I'm from Scotland. And remember the Maclaurin, our center is 0. Use the Maclaurin series for sine of x to approximate sine of 1 so that our approximation is less than 1 over 1,000 without using your calculator. So the first part is we want to go with less than 1 over 1,000. And then we want to justify that our error is less than 1 over 1,000. Now you might recall yesterday that the Taylor series for sine of function is an alternating series. So this is going to be our alternating series remainder test here. So for the first part, let's use our Taylor series to approximate sine of 1. So we're going to say sine of 1 equals, and I'm going to use my series, 1 minus, well, 1 cubed is just 1. 1 over, that's just 6. Plus 1 over, well, 5 factorial is 120 minus 1 over, and whatever 7 factorial is, I just know that that's 7 times 6 factorial, which is 720. And I already know that this part right here is already less than 1 over 1,000. So I can stop there. If you really want to know, that was 5,040. So I can stop here because remember, we want our approximation to be less than 1 over 1,000. And that, since it's an alternating series, we know that this is less than our next term. So we can now say with confidence that the sine of 1 is approximately 1 minus 1 over 6 plus 1 over 120. Now notice up here I put the equal sign because remember we were using our series, that goes on forever. But when I approximate, I put down approximately. Now, the next part says, how do I know that my error is less than 1 over 1,000? Well, recall, this is an alternating series. Right here, sine is just an alternating series. If you might remember that sine of x as an alternating series could be written as this, n equals 1 to infinity, or 0 to infinity. We could write it as negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. I think this should start at 0 right there. At 0. So this is an alternating series, and that's what we're going to use our remainder for. So we would say, use our mantra, even though we know it's alternating series, we have to define it. The series alternates, decreases in magnitude, and the limit equals 0. Therefore, our error is less than the next term, which was this negative 1 over 40, which is less than 1 over 1,000. Remember, this is my next term right here. Remember, this is my next term. That's my a sub n plus 1. But now we have to define it by the alternating series remainder. Whew. Right there. Okay, the next part says, use your calculator to find the actual error. Oh, that's not too bad, to get the actual error. Now remember, we're going to use magnitude. Now some of you guys on the quiz or on the homework, you keep this less than negative 1 over 40. We don't want the negative. We really want the error to be positive. Error is a positive value. It's a distance. It's how far off we are from the actual value. So to get the error, I'm going to take the actual answer, sine of 1, minus my approximation. 1 minus 1/6 plus 1 over 120. And I'm just going to type that into my ever-trusting calculator. So let's see here. Oops, doc B, clear it out. Alright, so I just typed it in, trig sine 1 minus, in parentheses, 1 minus 1 div 6 plus 1 div 20. Press enter, and I'm going to convert that to a decimal. And notice it's negative, but I want to make it positive, so it becomes positive 0.123196. I go out quite a few decimal places. And that's how far off our actual answer is from the actual value. And notice this is less than 1 over 1,000. So our error is good. All right, so let's take a look at another example. All right, now this is like an AP type question right here, where they're going to ask us to find the integral from 0 to 1 of sine of x squared, so that our error is less than 1 over 1,000. So again, this is our alternating series remainder. There's an alternating series remainder there. So we want to integrate sine of x squared. The problem is, oh no, we can't do this by hand. This is impossible. You won't be able to do this by hand. Some of you might be thinking, Mr. Warnow, hold my soda. I'm going to try this one. You won't be able to. You just hurt yourself. Don't be a hero. All right, so what we're going to do is we are going to use our series. So we know that sine of x is, and this is from yesterday, just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. Well, we want sine of x squared. So sine of x squared. Well, everywhere there's an x, I just make it x squared. This is from yesterday's homework. X squared minus, this becomes x to the 6 over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus ... And now we're ready to integrate. All right, let's go have some fun. So now we're ready to integrate this. The antiderivative from 0 to 1 of x, whoops, sorry, not x squared, but sine of x squared dx. I can rewrite this as 0 to 1 x squared minus, I'm replacing it, since I can't do this, I'm going to replace it with my substitution, with what I can approximate it with. 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus ... and at the end, dx. There's a dx there at the very end. All right, so let's go ahead and integrate now. When we integrate here, this is going to become x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial plus dot, dot, dot. Now I'm going to stop there because I'm probably already, if you look at the value here, what's 11 times 5 factorial? That's way less than 1 over 1,000. So I could probably stop here right now. And we would evaluate that from 0 to 1. Using our fundamental theorem right now, we would get, plug in the ones, we would get 1/3 minus 1 over 7 times 6 plus, this is just 1 over 11 times 120 plus dot, 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 minus, and all the rest just becomes 0. So I can take a look right here. I want my error, remember, to be less than 1 over 1,000. So look right here. The AP doesn't expect you by hand to know what 11 times 1 over 120 is. They know that that's less than 1 over 1,000. Right here, we know that this is already less than 1 over 1,000. So we can stop. And now we can write our answer. Therefore, our approximate value of sine of x squared dx is approximately 1/3 minus, and if you want to, what is 7 times 6? 1 over 42. And now we want to guarantee that it's less than this. Well, that's our alternating series remainder. The series alternates, decreases in magnitude, and the limit equals 0. Therefore, our error is less than 1 over 11 times 120, which is less than 1 over 1,000. Remember my next term, by the alternating series remainder. It's a big rule for us. And this would be our answer. Now don't forget that here, right? Remember this right here? That's my next term in my series. So we can approximate this integral with an error of less than 1/1000th of the actual answer by just going out how many terms? Just 2 terms. That's how accurate this Taylor series is. All right, now let's find the actual error in the approximation. So to get the error, don't forget, we're going to take the absolute value from 0 to 1, sine x squared dx, minus our approximation, 1/3 minus 1 over 42. And let's go and type that in our calculator right here. So we're going to go menu 4, 3. If you're using the CX, you'll see menu 4, 2. From 0 to 1. And this becomes the sine of x squared, sine x squared dx. Now here's the ironic part. Your calculator is actually using a series to approximate its own value, and we're using it to find the difference in the actual value in the series itself. I know the irony, right? Minus, but parentheses, 1 div 3 minus 1 div 42. Press enter, and oh my gosh, we get, what's that? 0.12374, something like that. It's crazy accurate. Look at that. That's our error. That's the actual error from the actual value. That's like what, 74 10,000ths? 74 100,000. I can't read decimals. All right. So I hope you enjoyed this video. Go to number 2, and we'll take a look at some more examples. See you then.